Welcome to part 2 on the series regarding development of models of force deflection relationships for planar rigid body mechanisms. This is part 2. We're going to have a look at how do we calculate the number of degrees of freedom that a mechanism has. In the first part, we looked at how these topics relate to your semester project. We looked at the fundamentals of kinematics. And then after this, we're going to look in more detail at this concept of mechanical advantage and bring everything together finally and develop some force deflection models. The objective for part 2 is to learn how to evaluate the number of independent mechanical degrees of freedom for a planar mechanism. Reviewing mechanical degrees of freedom for a rigid body in 3D space, we have 6 degrees of freedom, 3 translational and 3 rotational. When we connect rigid bodies using joints, this removes degrees of freedom. So for example, if we take a 6 degree of freedom system and restrict it to motion on a plane, that removes 3 degrees of freedom, so there are only 3 left. Another example is 2 rigid links in a plane. Each have 3 degrees of freedom, 2 translational, 1 rotational. So combined, they have 6 degrees of freedom. But if we were to connect them using a revolute joint, that removes 2 degrees of freedom. We have just 4 parameters that are required to uniquely describe the position of the linked system. So with this observation, one might think there's maybe some systematic way of evaluating how many degrees of freedom are in a system based on the number of links and also the number and types of joints. So for example, if we add a revolute joint, that removes 2 degrees of freedom from a system. So let's talk about how to actually go through these calculations. We want to know how many unique parameters are required to describe the position of a mechanism uniquely. This is Kutzbach's equation. This is a variant of Grubler's equation. This is a form that works well for the topics we cover in this class. And we want to calculate this for planar mechanisms. It's more complicated to expand to spatial, 3-dimensional mechanisms. Planar mechanisms are sufficient for this course. M is the number of degrees of freedom. L is the number of links. And if you see in the equation, we subtract 1 from L. And that's because we assume with a mechanism, one of those links is the ground. Now remember, the difference between a kinematic chain and a mechanism is one of the links is grounded. So pay attention to this in that you have to remember to count the ground when you are determining what L is. J1, that is the number of full joints. We talked about full and half joints previously. Full joints are the types that allow only 1 degree of freedom. So for example, pin or revolute joints or prismatic joints. J2 is the number of half joints. 2 degrees of freedom are allowed. For example, the pin and slot joint that we reviewed last time. So take a look at the coefficients for this equation. If we look at J1, we multiply it by 2. So based on the observation in the last slide, this should make sense. If we added a revolute joint, a full joint, to the system in the last example, it removed 2 degrees of freedom. So for every full joint we add, we subtract 2 degrees of freedom from the total number of the unlinked system. And then for J2, each joint we add that's a half joint, we only subtract 1 degree of freedom. Here's an example of a serial planar manipulator, robotic manipulator. Say we have 3 links, 3 revolute or pin joints, and it's grounded. So if we count the ground, L is equal to 4. The number of full joints is 3, the number of pin joints, and there are no half joints in the system. If we apply Kutzbach's equation, we can determine that the number of degrees of freedom in this mechanism is 3. Often we're interested in defining some type of generalized coordinates to define the position of a mechanism, one option for doing this is to specify the 3 joint angles for this mechanism as the coordinates that we can use. In the last video, we talked about robotic systems and kinematics and introduced some of this terminology where these coordinates, these generalized coordinates that describe the position of a mechanism, in robotics terminology, the coordinates would define the configuration space. So the value of theta 1, theta 2, and theta 3 combined is a point in the configuration space. But then the physical workspace is the actual physical space that this robot is in. And in kinematic analysis, we're interested in translating a point in the configuration space to a point in the workspace. Here's another example. This is a pin in slot joint. We've already defined previously that this is a half joint, that it allows 2 degrees of freedom. And we can use this as an example to test Kutzbach's equation. We can look at this joint in a somewhat different way. We can see it as the combination of a prismatic joint plus a revolute joint. So to be more precise, let's define what the links are. Here we have this slot as a link, and here we're saying that's grounded. And then we can have a slider, an independent link that slides in that slot. That's another link. And then finally, we have the link that connects to the pin joint that can rotate. That's the third link. We can identify the joints as well. We have the prismatic joint that constrains the relative motion between the slot, the grounded link, and the slider. The second joint is the revolute that connects the slider and the link and constrains its motion. So let's apply Kutzbach's equation and see how many degrees of freedom it predicts this system will have. The number of links is 3, including the grounded link. The number of full joints is 2, and the number of half joints is 0. If we plug the numbers in, we verify that the number of degrees of freedom is 2, and that agrees with the earlier statement. Let's look at a few important concepts regarding degrees of freedom. What if Kutzbach's equation produces something other than a strictly positive integer? What if it's 0, or what if it's a negative integer? So if m is greater than 0, that's the usual case when we're analyzing mechanisms. That means there is at least 1 degree of freedom, one way that the parts of the mechanism can move relative to each other. But what if m is equal to 0? What does that mean? That's a structure. There's no rigid body relative motion possible. Everything is fixed. But what if m is less than 0? Well, that essentially means it is over-constrained. We have more constraints than the minimum required to prevent motion. And this is what we would call a statically indeterminate structure. And to determine the forces in a statically indeterminate structure, you might remember you need to combine not only the equations from equilibrium, from statics, but also equations from elasticity. So if we have the case where m equals 0, that is a statically determinate structure. So if we have, again, the case where m is less than 0, the magnitude of m plus 1 is the number of constraints we would have to remove to allow any rigid body motion. So for example, if m was equal to -2, then we would need to remove 3 constraints from the system to allow rigid body motion. Let's have a quick look at the relationship between degrees of freedom and robotic systems. If NA is the number of independent actuators, things like motors or solenoids that can be used to move components in a robotic system, and if the number of actuators is equal to m, the number of degrees of freedom in the mechanical system, then we say this is a fully actuated system. That means we can actively control all degrees of freedom in the robotic system. Now, if the number of actuators is less than the number of degrees of freedom, we call this an under-actuated system. So this means that we cannot control actively all degrees of freedom. Some degrees of freedom are going to be governed instead by passive dynamics. If we have the number of actuators greater than the number of degrees of freedom, that's an overactuated system. This provides some redundancy and flexibility and control strategy, but to make this work, we have to determine sets of control signals that are compatible with each other. Otherwise, we're going to have problems with the system. Let's look at another example. The trailing arm suspension from the project can be simplified a bit and analyzed for the number of degrees of freedom in the system. I want to point out here in this video just a few things about the configuration of this system in the semester project, mainly because we're not really considering dynamics of the system. We're not looking at the details of the damper. But in pretty much all suspension systems, there is some kind of damping element to help damp out vibrations. And one possible configuration for a damper is to have coaxial spring and damper. So the spring wraps around the damper and they have the same axis of motion. And that's what we're going to assume is the case for our system, although we don't really need to include the damper in the calculations for the semester project. Having a damper in a suspension is important for stability and also to tune the dynamics of the system to get good performance. Because the damper and spring are in parallel with each other mechanically, they are going to have the same deflection and the same velocity, and that's going to be important later in some calculations. One simple damper model that's used is this proportional model where we say the force across the damper is equal to a constant, c, the damping constant, times the velocity or the rate of change of distance between the ends of the damper. In reality, dampers are not linear. If we look at this force velocity plot, the dependence of force on velocity is usually nonlinear. In a typical damper, energy is dissipated through complex fluid flow through some system of valves or other passages that restrict viscous fluid flow inside the damping system. Okay, back to the suspension analysis. We can simplify the description of this suspension looking at the vehicle frame as the ground and the trailing arm connected with a revolute joint to the vehicle body, and we apply a force at the bottom of the trailing arm. But then we have the coil over spring and damper assembly connected between the trailing arm and the vehicle frame. Let's have a look at the links in this system. Link number 1, the vehicle frame. We are assuming that's stationary, that's the ground, and we're looking at the motion of the wheel moving up relative to the vehicle frame. Number 2 is the control arm or trailing arm. Number 3 is the lower portion of the coil over assembly. So this requires a little bit of explanation. The distance between attachment points at the two ends of the coil over changes as the suspension moves up and down, and we're going to model that change in distance as two links connected by a prismatic joint. So the first of those links is link 3. The second of those links is link 4, the upper portion of the coil over assembly, and those are linked with a prismatic joint. So they can move relative to each other with just 1 degree of freedom, and that's going to model the change in length of the coil over spring and damper assembly. Let's have a look at the joints. Joint A, that's the trailing arm pivot. It's a revolute joint. It allows 1 degree of freedom. The lower spring attachment is also a revolute joint. The prismatic joint that represents the compression of the spring and the damper, that provides 1 degree of freedom. And finally, the revolute joint at the top of the coil over assembly this upper spring attachment that provides an additional degree of freedom. Now, if we count up the number of links, including the ground, the vehicle frame, we have 4. The number of full joints is 4, and we have no half joints. Applying Kutzbach's equation, we find there's 1 degree of freedom, and this is what we would expect for a suspension system. I should point out there are a number of special cases, and we're not going to get into detail with that in this class, but you should be aware that Kutzbach's equation does not always work. Sometimes the value of m does not always match up with the actual number of degrees of freedom a mechanism has. But these really are special cases. So for example, in the upper figure, it's a structure, and that's what Kutzbach's equation would predict. The number of degrees of freedom is 0. But if we were to change the geometry of the links such that 3 of them are in parallel, then this would permit 1 degree of freedom, and this would be a mechanism, even though Kutzbach's equation predicts that it would be a structure. I'd like to point out an important link to later topics we're going to cover in the course. It's important that you understand this concept of degrees of freedom when we cover the section on structural steel design. We're going to talk about something called collapse mechanisms. This is a failure mode. That's an important one for you to learn how to analyze for structural steel systems. This is especially important for structures that involve beams with an internal bending moment and beams that are over-constrained, or in other words, statically indeterminate structures. There are a number of ways that a collapse mechanism could form and lead to failure. We need to know what is the degree of static indeterminacy. What is the value of m? How negative is it? And that's going to tell us, well, how many what we call plastic hinges need to form before a collapse mechanism forms. And there are many different ways usually a collapse mechanism can form, and so you'll need to go through a combinatorial analysis of the different ways a collapse mechanism could form and identify which one is going to be the weakest. This is going to be an interesting topic coming up where the analysis involves an additional type of nonlinearity. So here we have so far been talking about nonlinearity due to nonlinear kinematics. Another type of nonlinearity that comes up is material behavior nonlinearity. And in this case, we're going to be looking at plastic material deformation in the section on structural steel design. To summarize part 2, we reviewed the concept of mechanical degrees of freedom. We introduced Kutzbach's equation as one possible way of calculating planar mechanism degrees of freedom. We demonstrated degrees of freedom calculations using several examples. We looked at a robotic manipulator, pin and slot joint, and a simplified trailing arm suspension. For the final video, after this, we're going to have a look at the concept of mechanical advantage and then combine everything to derive complete force deflection models. And this is what you're going to need for both your homework and also for project deliverable number 1. Thank you.